welcome. It is a distinct pleasure and a great honor to introduce today's speaker, Professor Reinhard Genzel. Professor Genzel is one of the world's leading pioneers in observational astrophysics. For more than 4 decades, he has helped define modern observational astrophysics through a combination of scientific vision, of technical innovation, and of sustained leadership. His work has profoundly shaped several areas in our field, from the physics of the galactic center, of course, to star formation, the interstellar medium, active galactic nuclei, and the coevolution of galaxies and their central black holes. For his leadership and his achievements, he's the holder of an extraordinary record of distinction, including, just to name a few, the Stern-Gerlach Medal, the Albert Einstein Medal, the Shaw Prize, the Karl Schwarzschild Medal, the Crawford Prize, the Tycho Brahe Prize, the Herschel Medal, and the 2020 Nobel Prize in Physics, for providing compelling evidence that a supermassive black hole resides at the center of our own galaxy, the Milky Way. It is this fascinating journey that he will talk to us about today. Professor Genzel, I speak for all of us at Forth and the University of Crete when I say it is a true privilege for us to welcome a scientist whose work has so fundamentally deepened our understanding of gravity, black holes, and the very heart of our galaxy. Dear colleagues, dear friends, thank you all for being here today. Please join me in welcoming Professor Reinhard Genzel. Because we're so sure that your lecture is going to be fantastic, we're going to give you the gifts ahead of time. So we have here a coffee table book with pictures taken from Skinnacus, which, as you know, the Max Planck Institute for Extraterrestrial Physics has helped found. And we are always very grateful for that. And it is a signature of our joint journey in science.
Thank you.
It's called The View to the Universe.
Great.
And we hope you enjoy it. Yes, it is the symbol of the Foundation for Research and Technology, the Festus disk, which still to this day is a puzzle that defies solution. So you're very good at puzzles and you're very good at making progress and unsolved mysteries. So, you know, we thought we'll give you a chance.
Look, this is wonderful because when I was young, I wanted to become an archaeologist. And the first time I was in Crete in 1976, I was already looking at all the wonderful, wonderful sites and also in other parts of Greece. I had in school 6 years of Greek, or ancient Greek, yes, and I enjoyed it enormously. Your forefathers and foremothers really shaped Europe, and you did a fantastic job. Thank you for having me.
Thank you very much. The floor is yours.
Thank you. Okay, I guess, Kit, we have the lights off here in front. So I'm sure you're experts in all of this. I'm sure you've seen the movie Interstellar. And so who am I to tell you about black holes? You know everything already. But actually, this is not anymore a science fiction question. It's really an issue of modern experimental physics, as well, of course, as theory. I will start with that a little bit, because all of this started, if you like, 300-400 years ago, but then certainly 110 years ago with Albert Einstein presenting his new theory, for which he didn't have a solution actually at that time. But a year later already, Karl Schwarzschild found the first solution, and that had in it a singularity of density of material, and that is a black hole. So since that time, initially the theorists and then also the physicists for sure, but definitely the astrophysics community has been asking the question, are these objects which general relativity predicts, do they really exist? And so I got going on this when I was in California as a young postdoc initially, and then also a professor with a very famous physicist as my mentor, Charles Townes. I'll show you him later. And we started following up on that question by looking at what would be the nearest example of black holes. Now, this kind of work you don't do in a night. You don't do it in a year. It took us about 40, maybe even now 45 years, with many young people, in fact, from everywhere in the world, including Greece, to research that and really find ever more convincing evidence that these objects predicted by Einstein's theory really, truly exist. And so that's the story I want to tell you about. Now, this is very closely connected to the other question which we are active in, namely, how did these objects in which we have our home and called Milky Way or galaxies in general terms, how did they form and how did they evolve? And what about the black holes and the galaxies together? So that's the story which I want to start with by taking you on a trip out of the Milky Way into the nearby universe. You see the stars in the Milky Way, nebulae, where stars have exploded or form new stars. You see the dark stretches of interstellar dust, which attenuate optical and ultraviolet radiation. And then when we travel here into the center of our home galaxy, we see the nucleus back there, the light concentration. Now we are flying at 10 to the 12 times the speed of light here out of the Milky Way. There it is, our home galaxy, a beautiful spiral galaxy with 600 billion stars. And as you will see, also black holes. That's the nearby universe. There is the Andromeda Nebula, which also has a black hole, as we now know, and so many other millions and billions of galaxies. And astronomy has had a fantastic time in the last 100 years to explore this universe of ours, initially nearby, and then as we went, and now ever further away, and therefore, because the speed of light is finite, back into the past. To the time when, in fact, our universe started in a very hot state we call the Big Bang. Now, all of this is intimately coupled then with the question of what keeps the universe together, Milky Ways, et cetera, et cetera. And that's, of course, gravitation. And we humans, including your Greek forefathers and foremothers, knew about gravitation. Every one of us knows about gravitation. When you jump up, you're sure to know that, 0.3 seconds later, you're back down on Earth. You cannot escape the gravity of Earth. And the planets around the sun are kept in their orbits by the gravity of the sun. And they are, as you know, and that we know through research of Galilei, Copernicus, Kepler, and Newton, they are on almost circular orbits. And by looking at these orbits and measuring the speed of the planets, together with the theory of gravity, initially by Newton and then later on, of course, by Einstein, you can actually measure directly that in the center there must be a mass, even if that mass would not radiate. There's one solar mass of material in the center which keeps these planets on their orbits. And that is, so to speak, the way to measure gravity for us. We go ahead and look for distant objects, and then we measure not planets, but gas and stars. And you will see how we do this in order to then ask the question, is there a central object? What is its mass? And how compact is it? Now, the story of black holes is as old as the Einstein talk in December 1915 in Berlin, where Einstein showed his equations, but had only approximate solutions. But 1 year later, Karl Schwarzschild on the Eastern Front in World War I actually found the first solution. And it's absolutely fantastic if you look what he wrote to Einstein about the solution, because it has in it already the singularity of a black hole. If the mass and the size of this object are such that there is a critical mass to size ratio above which even photons cannot escape. And that's the key thing. Newton didn't know that. Newton did not think that light was affected by gravity. But Einstein, of course, knew that because of his equivalence of mass and energy. And so H nu equals mc squared. You may have, if you're close to physics, have heard that, of course. So the theorists explored these equations for a total of 50 years and found out ever more about it. There can be the mass, that a mass defines automatically that there is a region within which light cannot escape. And if you think about the sun, and you have a rocket on the surface of the sun, and you want to fly the rocket to large distances, then there has to be a minimum speed, the escape speed. And on the sun, that would be, if you could do that experiment, 600 kilometers per second. It's already pretty large. Now, on the Earth, that velocity is 11 kilometers per second. And we can do that now, of course, with our rockets, flying them into large distances. Now, this escape speed, due to the gravity of the sun, depends on the mass of the sun, but it also depends on its size. So this is the sun as we know it, but suppose in a Gedanken experiment, we make the sun much smaller, say less than 3 kilometers. And then we can use the same equations to deduce from this that the rocket now would have to take off with more than 300,000 kilometers per second. Oops, that's a problem, at least for the physicists. At the time already, there were experiments by Michelson and Morley, which knew that the speed of light is the fastest communication, and it's in empty space, 300,000 kilometers per second. And anything which would be required to be at that or greater speed cannot exist. So the conclusion mathematically is if you had such a sun, then there would be a radius, which we call the event horizon, within which even light cannot escape, nor any other particle. And if you go into such an object and you penetrate the event horizon, you will see that all of the energy is equivalent to mass, is combined in a central point, a singularity of infinite density. That's what general relativity predicts. But is it true? As scientists, and especially as physicists, we need to prove even wonderful theories like general relativity. And so that's essentially what's going on, and that's what I will tell you about. Looking for and then understanding very compact, high-density masses in the universe, and then asking the question whether they could be black holes. And then the next question is, what is the role of these black holes in the universe? Is there just one, or is there many? And how did they evolve over cosmic time since the Big Bang 13.77 billion years ago? So that's what this talk is about. Now, when you have an object which you would call a black hole, then of course, if you want to make measurements on it, you cannot use normal photons, right? We just learned that the photons cannot escape. But you can do the planetary experiment. You can use other masses surrounding this object and feeling the gravity to infer the mass and the density of the central object. So here's the solar system again, in this case with the central black hole. And then we would have to measure the masses surrounding that at different distances moving, and from that inferring the properties of the central mass. And that's what we have done in the center of our own galaxy, because that's really the closest galactic nucleus we have, and one where we can hope with the methods we have available to come so close to the central object that we can distinguish a black hole nature from any other. Now, this started all in the 1970s. In the 1970s, the radio astronomy community was able for the first time to measure out the distribution of radio emission towards the center. And you see that in the upper left there. In the horizontal direction is the plane of our Milky Way. And you see in the very center, there's a very bright region. And if you resolve this with techniques which we have available, there is a cluster of stars, which in the central picture are these blue points. And in the center of that, there is hot gas. Pink is ionized gas, and green is neutral gas. And at the center of this gas concentration is a radio source, which is very, very concentrated and compact. And so it's, you know, a possible explanation to say, well, maybe that object in the center, the Sagittarius A star, might be a black hole. How heavy would it be? And how do we measure this? Now, in Berkeley, at that time, a very great physicist in the 1970s was starting a second career. This is Charles Townes. He's the inventor of the maser and the laser and got the Nobel Prize in '64 for that. But then later on, he felt he should move on and do astronomy. And he built a group in Berkeley, and I joined that group. John Lacey was another one, and we started measuring the motions of these gas clouds. The pink gas clouds in various orbits, and the green gas clouds more or less in a tilted ring in rotation. And from that, we could learn something about the mass. So we measured the distribution of mass from these gas clouds and inferred that if you plot the mass in logarithmic units on the vertical scale and the distance from the source in horizontal scale, again, logarithmic, then if you go very far away from Sagittarius star and go inward, there's ever less mass. And that's because the star cluster around the galactic center dominates, and that's, of course, an extended mass distribution. But once you measure closer than about 3 light years, 1 parsec, the mass stays approximately constant. So that's what Charlie Townes and his group, me included, found, and we were very bold and wrote a Nature paper on the mass distribution in the galactic center, and there we were saying, well, this is consistent with a cluster around a black hole of a few million solar masses. Now, in science, just because you say something doesn't mean that everyone else believes it. And so nobody believed us. Everyone said, oh, well, okay, yeah, this is much too far out, plus gas clouds can be pushed by forces other than gravity, so this is no good. So then I, in fact, moved from wonderful Berkeley to Munich and started my group in Garching near Munich. And we started building new instruments to be able to measure not the motions of gas, but the motions of stars. And that happened in Chile, in the very large telescope in Chile, the Atacama Desert. The Atacama Desert is really, this is really a desert. There is nothing. Very dry, beautiful skies because the air coming from the ocean gets rid of all of its water vapor near the coast, where there's a cold current, the Humboldt current. And here are some mountains, and there on one of these mountains, the European Southern Observatory has its first big observatory since 1995. 4 8-meter telescopes, a very large telescope. And with this privileged situation, because the galactic center here comes overhead in Chile, we were able to use these telescopes over time, building ever better and sharper instrumentation to image and also do spectroscopy of the central region. Later on, we went from a single telescope to combining all 4 8-meters to what we call interferometers. It's like radio astronomy, only about several thousand times more difficult because of the short wavelength. So that's it. That's the so-called very large telescope. And we developed techniques like adaptive optics to make the pictures sharper because the waves, as they penetrate the Earth's atmosphere, get distorted by the atmosphere. So you correct them by shooting up lasers into the sky that gets reflected, and then you use the reflection to sharpen the images to the sharpest you can. And that is the so-called gravity instrument, which we've been using for our work. Now, the galactic center in many ways is sort of one of the cornerstones of asking the question about massive black holes. So I told you there's a very dense star cluster. In the center of that, this green dot is the radio source. And our group in Munich, you see Frank Eisenhower and Stefan Gillison, and Andrea Gess's group at UCLA with the Keck telescopes in Mauna Kea started a competing race, California against Europe, so to speak, and to measure the motions of these stars, the same way I've described to you before. And indeed, after about 6-7 years, you saw the first comprehensive set of motions of these stars. And nowadays we can do this in extremely good resolution. And we can see stars moving around the radio source on the scale of the solar system. And that is only a few thousand times the event horizon of a 4 million solar mass black hole. And indeed, these motions you see here, you can analyze in great detail and show that the mass is completely determined by a central mass of 4 million solar masses located right on Sagittarius star. And so that's the sort of the playground we've had. Now, this doesn't happen overnight because these stars, these orbits you see here, typically take 50, 80, 200 years to go once around. And so we were able to do this, and so was Andrea. And so for this, then we were able for some stars to get complete orbits. You see in the upper left there is one star which is on a highly elliptical orbit of 16-year time and comes close to the radio source, which is that black dot there in the lower part of the image, where the star moved at about 7,500 kilometers per second. So that's 2,000 times the speed of the Earth around the sun. And so by measuring these motions, you could derive that the mass of 4 million solar masses must be contained to a region less than the orbital radius of Neptune. Okay, so that's already very unlikely to be anything but a black hole, but it doesn't have to be. You could imagine some other configurations. So then we started using these data to test general relativity in this regime. So for instance, if a Sagittarius star emits light, or stars in this region emit light, then as the light goes towards us, it loses energy. That's called the gravitational redshift. That's what general relativity tells you to see. And indeed, if you subtract the Newtonian orbit, this is the horizontal line, general relativity predicts this red orbit where the shift is about 200 kilometers per second when the star is closest. And indeed, that's how the data obviously can be described. The next thing, we wanted to go closer and found that every few days, Sergei star, that radio source, emits a flare of infrared millimeter, submillimeter light, also sometimes X-rays. And when you use the interferometer and on these, you see it's polarized infrared emission, and it moves at 30% the speed of light, only a few times the event horizon. And from the speed, you can then infer that is the same mass we see with the stars further out, but now all within a few times the event horizon. And the next thing is general relativity predicts that if you have a star, say, moving around a central source in Newton, if there's no perturbing third object, that orbit always is the same in space. Not so in general relativity. In general relativity, there's two effects. One is the star precesses clockwise forward. That's called a Schwarzschild precession. And that in the galactic center, we were able to also measure. You see below, we subtract the Newtonian orbit again and look at the residuals. If it would be Newton, well, then they shouldn't see any residuals, but we see these loops, and that's the Schwarzschild precession of the orbit. Then there are more effects which we haven't yet fully tested. One is if the central object is a black hole, it can have spin, and the spin can induce another precession called an end-steering precession, and that's the next 30 years for us to measure that, because it's really a difficult measurement, depending also on how large the spin of the black hole in the galactic center is. So that's our laboratory. The radio astronomers can also look at this wonderful radio source, but with much higher resolution, because they can nowadays build interferometers at very short millimeter wavelength and spanning telescopes across the entire globe. With that, they reach angular resolution, which is only about 2 times the event horizon size. And indeed, then you would expect, if you're observing Sergei star there from on the right side, and there's a source of light behind the black hole, then of course, some of the radiation can pass through if it's far away from the black hole. But if the radiation is closer, if it's very close, it falls into the black hole. If it's a little further out, it gets, so to speak, on loops around the black hole. And so you would expect a dark central spot surrounded by a sort of a shadow of a bright ring of radiation. And indeed, in 2022, that's what our colleagues published. And the size of the ring is immediately a telltale of the mass. Now, we know the mass from the orbits of the stars very precisely, to 0.1%. And so we can predict what that size of the shadow should be, and it should be 52 microarc seconds. And what do our colleagues measure? 51.8 microarc seconds. Well, there's still some substantial uncertainty, but still, this is a direct confirmation of what we have, but also of the speculation that this is a central black hole of about 4 million solar masses. So after about 40 years of measurement, we have been able, and also our colleagues, to push the mass determination in the galactic center to ever smaller scale. Initially on the scale of light years, then measuring the motions of these stars you have seen, and then lately also the central region with this with a star which is only 100 times the event horizon size, and then these gas clumps and the shadow. With that, we can basically say the mass is always the same, but it's essentially a point mass with respect to our measurement. In fact, you can ask the question, what else could there be outside of the central mass? And it turns out if the central mass is 4.3 million solar masses, outside of it in the vicinity, there cannot be more than 1,000 solar masses. That's incredible. In fact, quite unexpected. Picture always had been that if you have a black hole, then the black hole pulls on the stars and brings them close to it in a so-called cusp. There doesn't seem to be much of a cusp. So that tells us that the efficiency of destruction of stars as they fall into the black hole is very, very great. Anyhow, so this is 2026, and we are again happily measuring down in Chile right now to observe that star S301 and hopefully measure the spin in a few years. Again, won't happen overnight. You have to have patience, excited young people who basically work in a team on very complicated experimental stuff, but it has been fun and continues to be so. Now, in the local universe, others have looked for other active, we say, galactic nuclei. So these are bright central spots in galaxies, much further away than the Milky Way, but still in the local universe. And they find very bright central regions often, and some of them are extremely bright, those we call quasars, also variable. And so you can measure, infer the mass on the vertical scale again, versus the mass of the central part of the galaxy, which is on the horizontal scale. The galactic center is that green little dwarf object with 4 million solar masses. But there are, dear to us, only a few tens of millions of parsecs away, galaxies which have 10 to the 9 solar masses in their centers. So that's much, much more massive than the Milky Way. So these black holes seem to be very typical in the centers of galaxies. And since there is a correlation with the mass of the galaxy, that indicates that they've had a process of growing, which was coupled, a co-evolution, as we say, over cosmic time. And with the James Webb Telescope, we can now, in fact, go back and look at these processes happening in early galaxies. Material from the intergalactic and circumgalactic medium is drawn into the mass of the growing galaxies, and some of it forms stars, most of it forms stars, but about 0.3% of the inflowing material forms active galactic nuclei, black holes. So this co-evolution is a fantastic thing, and the James Webb Telescope has now shown to us that this correlation is present even in galaxies which are only a few 100 million years, not billion years, million years after the Big Bang. So that's something which we need to understand. We have no idea how these black holes and the galaxies could grow that fast in the early universe. There must have been other processes than these flows of accreting gas in the later periods. Now, theoretically, you can understand this kind of growth if you understand that the dominant material in the universe is so-called dark matter. It doesn't radiate. And then over time, the universe expands, and there are regions of overdensity of dark matter which then attract normal material, and they form these filaments. And at the centers of these filaments, you then form these galaxies, which grow over time, form stars, black holes. And then sometimes, around 2-3 billion years after the Big Bang, these galaxies, these active galaxies become so powerful, they start to eject material again, jets, winds, and all of a sudden, heavy metals and heavy atoms get thrown out into the intergalactic medium. Here you see this in these simulations. So black holes and their evolution and galaxies and their evolution over cosmic time seem to be closely coupled. And we want to understand, in fact, what happened in the earliest times now. So we will still have to improve our instruments further and go the next step to look at these galaxies and their galactic nuclei, you know, at the regime of only a few 100 million years after the Big Bang. That's going to be a challenge. But we are building a new telescope in Chile, the so-called extremely large telescope, which is 40 meters in diameter. Very powerful. There it is. If you would travel there now, you would be impressed. A 40-meter diameter telescope, together with its dome, is 100 meters across. It's like a football stadium. Incredible. We have colleagues who use gravitational waves to follow the same path, but with different means. As you have masses move, they distort space-time. And so by measuring the distortion of space-time, we can then infer the central masses and their diameters, just as we do from the motions of stars. And in hopefully 10, 15 years, the European Space Agency will fly such an interferometer in space of 3 big stations, 2 million kilometers apart from each other. And they could see the infall, the in-spiral of stellar black holes into a massive black hole, all the way to the event horizon of the massive black hole, and test the most critical fundamental prediction of general relativity, that there are only 3 quantities you have to know about galaxies and masses. One is the mass, one is the spin, and the third one is the charge. Now, if you forget about the charge, that means all other qualities of these black holes are contained in the spin. These are very simple objects. If you want to describe the Earth and its gravitational potential, you need hundreds of terms. Why? Because there are mountains and valleys and water and so forth, not on black holes. They are very simple objects. And so that is the experiment that we want to have work out maybe in 30 years from now. You young ones have a chance, jump in and go along on that trip. It's going to be fantastic. You see, I'm now an old man. I'm 73 years old, but I'm having a lot of fun. Yeah, I don't know that one. Okay, all right. Black holes.
Question. Yeah.
Well, you have mentioned that for such massive black holes, there is no idea of how they were formed. So I would like to ask of course, this is the first order approximation to this. What are the theories about it?
Well, I mean, the standard explanation is, well, you have a black hole and there's material around it, lots of material, and the material is attracted by the black hole. But now, of course, it can't just go straight in because of the conservation of angular momentum. So you have to have friction. We believe nowadays that this friction near black holes is magnetic fields. So it's ionized gas, or the transfer of angular momentum to the magnetic field is the key feature. But then there's also, in addition to gravity, there is another force here, and that's radiation pressure. So as you convert, a significant fraction of the mass into radiation in a accreting black hole, there's a lot of photons, and they push against the incoming gas. And so there's a very well worked out theory, which then says that under normal circumstances, black holes cannot grow more than a factor of 2 in 400 million years. So the objects which James Webb already has seen only 100 million years or 10 million years after the Big Bang, it's just doesn't work. Now you can, escape this conclusion in various ways. One is you have the material, fall in this way and the radiation go out the other way. That's not so stupid, and get to larger than what we call Eddington accretion. Another way to do this would be, of course, to have other processes. And there are lots of theorists right now thinking about these processes which could have happened. One of which is that already in the Big Bang, black holes were formed. Now, this is actually a proposal which Stephen Hawking made in 1971 already, but it was later rejected because the black holes you would expect from this process are very, very small masses. And so it's unlikely that they are then turned into big masses. So we are guessing. And what we will do is we will use our machine to now look at quasars and look at the motions of material around them and really check it out experimentally. So let's get together in 40 years and then report.
Thank you for beautiful lecture about black holes in our galaxies, and thank you for precise plots about inhomogeneous density in galaxies. So if you closer to the center, you have bigger density. But also we know due to modern exploration that, thank you very much, that in the beginning of universe, our density also was inhomogeneous due to cosmic microwave background. And I'd like to know if our universe in the beginning was uniform and all particles in the universe has the same velocity. We don't have black holes in this case. And if you have larger inhomogeneously in the beginning of universe, we will have more black holes right now. Is it possible to state?
Yeah, well, what you're saying is right. I mean, initially you would say it's not possible, but then it is possible theoretically that in the Big Bang you get fluctuations such that you form relatively small masses of black holes. Then you can basically speculate, well, maybe they started interacting and growing together through collisions. Okay, it doesn't have to be accretion. But none of this is really worked out, and certainly absolutely none of this is experimentally verified, and that's what we have to do in the future. On the one hand, a better theoretical framework, on the other hand, more experiments.
Okay, thank you for your answer.
I understand that the central black hole of our galaxy is a few million, 4 million, and whereas for other galaxies, it's closer to 1 billion. We might not understand the formation of even this one. Do we understand why we have such a large variation?
Well, I mean, that's the correlation between the galaxy mass and the black hole mass, which I showed you. It's sort of a hint, because they both grow through accretion from material further out. So if you grow the galaxy, you have a chance to grow also a bigger black hole. And so the biggest galaxies therefore have the biggest black holes. But now this correlation is not one-to-one. I mean, it's not a simple thing. And then there's a discussion, of course, is the accretion due to thin flows, or is it due to collisions between galaxies? In fact, in galaxies which are about 2-3 billion years after the Big Bang, where they're really already pretty massive galaxies, we are now able to measure the flows in the galaxies, and they are astonishingly large. There are spiral galaxies 3 billion years after the Big Bang, very massive ones, and they attract material at speeds which are unheard of in the local galaxies. And that shows you that there were growth processes which are much more efficient than nowadays.
Perhaps a quiet central black hole is
Oh yeah, that helps. I
Right.
mean, if you have a very active black hole like a quasar, then in fact you can destroy your entire galaxy, or at least the interstellar medium of it. Indeed, that happens, but rarely, because we think that happens if two big galaxies collide, and then the angular momentum is taken away, and everything collapses to two black holes, which then merge to a single black hole with old stars surrounding them. We see these galaxies in the local universe. They are rare, but they exist. Well, maybe we have to, explore this again experimentally, whether that's a true possibility. Theoretically, this process, what we call a major merger, which was very popular 20 years ago, is not so popular anymore because the rate of such collisions is very low. But if you wait a little bit, how about 2-3 billion years? Then we will collide with the Andromeda galaxy, and then you can measure what's happening then and publish it and get a Nobel Prize for it.
Thank you for doing us this honor. And I would like to ask you, since we have confirmed that there exists a massive black hole in the center of every galaxy, could we expand this thought to galaxy clusters?
Well, I mean, galaxy clusters often have a very central massive galaxy. In that flight out of the Milky Way, in fact, you saw the Virgo cluster in the end, and that has as its central big galaxy, an elliptical galaxy called M87, and that has a surely massive black hole at its center, right? So, I mean, yes, in such clusters, you will find many black holes if you have many big galaxies in there.
But not a singular supermassive black hole.
Well, I mean, people have been looking, and they have been over time finding rare cases of objects with 10 to the 10 solar masses. But, maybe currently we have 10 of those or something like this. But if you make ever deeper searches for distant galaxy, which is happening right now with space instrumentation, James Webb and others, then I'm sure you'll find more of those. There's so many objects in the universe.
Yeah, first of all, thank you for your beautiful presentation. I'd like to ask what we could actually see in this beautiful, inspiring picture of the black hole itself. Is it the reddish, or probably it's not really red, but the ring you can see? Is this the accretion disk, or is this some lensed image of something that is in the back of the black hole? And especially, I remember 3 brighter dots are in this circle of light. What is this actually?
All of the above. So you would expect if there's a substantial amount of spin and a magnetic field, then it's very, very plausible to start a jet going out in opposite directions with almost the speed of light. We have not seen that in the galactic center, and that could be a marker of the fact that the galactic center black hole has not had much accretion. Because in order to get lots of ejection, you have to first accrete material into the, as you say, the accretion disk and to the magnetic surrounding. In the galactic center, in fact, this central region where we see these motions is highly magnetized. Magnetic density there is larger than the gas density. And that is the result of the fact that the galactic center has had very, very little accretion onto it. Then the other thing is, of course, how is the geometry? He thought always, since the galactic plane is like this, if you looked at textbooks, you would always assume the galaxy mass black hole has an accretion disk this way. Absolutely not. The central accretion disk is almost face on. Okay, and that is a result of the fact that the accretion does not come from the large scale of the galaxy. It's the local phenomenon where you know, on Mondays, a bit of gas comes from there, on Tuesdays from there, on Wednesdays from there, not very much together, and certainly not in the plane of the Milky Way.
Okay, thank you.
Thank you.
Have one more? Could we have one more question?
The last one, sorry for the question from humanitarian educated. So we have a massive galaxies because of massive black holes inside, or we have a massive black holes inside because of massive galaxies. What was the first, chicken or egg?
Probably both.
Both?
They grew together, yeah. Because the material which you use to build up the galaxy and the black hole comes from the outside. And in fact, the average piece in the black hole has had to lose all but 10 to the minus 9 of its original angular momentum, because it comes from way out there. And so it has to be so processed in losing angular momentum. Otherwise, it could not go through. So the process is coupled. Okay.
Thank you, sir.